Okay, ready for this? We're diving into the world of prime numbers today.
Prime numbers.
Yeah, prime numbers. We've got these excerpts from a book chapter all about how they're spread out. And let me tell you, it gets way more interesting than you might think.
Really? Prime numbers. I mean,
I know, right? They seem pretty basic, but trust me, there's a whole lot to unpack here.
okay, you've got my attention.
So we got these prime numbers, and they're kind of like the atoms of the math world, right?
Fundamental building blocks.
Yeah,
Yeah.
exactly. But the thing is, figuring out their arrangement, like their master plan, that's what's been puzzling mathematicians for, like, ever.
It's true. Some of the biggest brains in history have grappled with this.
Like, take Carl Friedrich Gauss, for instance. Talk about a math whiz.
Yeah.
Back in the 1700s, no fancy computers or anything, just pure brain power, and he was already all over these prime numbers.
Gauss. Yeah, he was trying to crack their code, basically. Imagine an infinite number line stretching out forever.
Okay, I'm picturing it.
He was trying to see if there was some kind of pattern, some predictable way to know where the next prime number would show up.
So it's not just about finding prime numbers, it's about knowing where they'll pop up next. Like, predicting the future of prime numbers.
Exactly. Think of it like, say you have this huge jar of marbles, millions of them.
Okay, lots of marbles.
And some are red, those are our prime numbers, mixed in with a bunch of blue ones. Now, picking out a red marble, not that hard. But could you tell me exactly when I'd pick out another one?
That's way trickier. So how do you even approach a problem like that? It seems unbelievably complicated.
Well, a long time ago, back in ancient Greece, they had this method called the sieve of Eratosthenes.
A sieve, like for sifting flour.
Kind of, yeah. It was a visual way to separate out the prime numbers. Worked pretty well for smaller numbers, but Gauss, he was playing in a different league altogether.
Aiming for the big leagues, huh?
Yeah.
So how do you even begin to figure this out? Did he come up with some kind of formula?
He did. He took that visual idea of a sieve and somehow turned it into a math equation, connecting how prime numbers are spread out to these things called logarithms.
Logarithms. Oh. It's been a while since high school math class. Remind me what those are again.
All right, so imagine trying to figure out how many times you'd need to double the number 2 to reach, let's say, 32.
Okay, let me think. Double once is 4, twice is 8.
You got it. So you keep doubling. Logarithms, they're what we use to figure out that how many times factor.
Right, right. It's all coming back to me now. So it's like, how many times do you multiply something by itself to get to another number?
You've got it. And Gauss, he found this link between how often these prime numbers appear and this idea of logarithms. Talk about a game changer.
So did he manage to find like a perfect formula, a secret code to pinpoint every single prime number?
Now that's where it really gets interesting. Even Gauss, with all his brilliance, couldn't find that perfect, always right formula.
No way, really.
It's true. What he did do, though, and this is huge, he came up with a formula that gives you a shockingly close approximation for how many prime numbers there are below a certain number.
Approximation. So it gets you close, but not quite all the way there.
It's shockingly accurate, really, especially when you're talking about big numbers. Basically, his formula says if you take any number and divide it by what's called its natural logarithm, you get a pretty good estimate of how many prime numbers are less than that number.
Natural logarithm. Hold on, is that different from the regular logarithm we were talking about?
You caught that good ear. Yeah, it's a little different, a bit technical. A natural logarithm, it uses this special number as its base called Euler's number.
Euler's number. Wait a minute, is that 2.7 something number I vaguely remember from calculus class?
That's the one. And you know what? We could spend a whole other episode just unpacking Euler's number and all its quirks. But for now, just know it's this special number that seems to pop up everywhere in math, even in nature.
You've definitely got me curious about Euler's number now. But let's get back to this prime number formula. I'm still trying to wrap my head around how a logarithm, even a natural one, helps us make sense of these prime numbers.
It all goes back to that sieve of Eratosthenes, that visual way of filtering out primes. What Gauss noticed was this: as you sieve out the prime numbers, they start showing up less and less the further down the number line you go.
So the bigger the number, the less likely it is to be prime.
Bingo. And the really cool thing about Gauss's formula, it doesn't just tell us that primes become less frequent, it actually gives us a way to measure, or at least approximate, just how much less frequent they become as those numbers get bigger and bigger.
So even though his formula doesn't magically pinpoint every single prime number on the spot, it does reveal this deeper pattern, this underlying structure in how they're distributed overall.
You got it. It's like he found a way to map out the landscape of prime numbers, even if he couldn't label every single landmark on the map. And what he did, it gave mathematicians this incredibly powerful tool, a way to understand how prime numbers behave on a much grander scale.
This is seriously blowing my mind. I'm starting to see why mathematicians get so captivated by these prime numbers. They're like the rule breakers, the rebels of the number world, constantly keeping everyone on their toes. But here's the thing. If Gauss, with that incredible brain of his, couldn't pin down a perfect formula, does that mean it just doesn't exist?
Now, that is the million-dollar question, isn't it?
It's kind of like, oh, well, it's a bit unnerving, right? But then again, it's also kind of exciting, you know? Like, are there limits to what we can actually figure out about these prime numbers, even with all the fancy math we've got at our fingertips?
That's the beauty of math, you see. It's not always about tying everything up in a neat little bow, finding those picture-perfect answers.
Right, right.
Sometimes the questions that really grab hold of you, that keep you coming back for more, are the ones that have been hanging around for ages, puzzles that no one's managed to crack yet.
So even though Gauss couldn't nail down that perfect formula for prime numbers, his work, what he started, it's been like this launch pad, helping us understand these mysterious numbers on a much deeper level.
Absolutely. His work on prime numbers, how they're
Yeah.
distributed, it's had this ripple effect, spreading out to all sorts of areas,
Yeah.
cryptography, computer science, you name it.
Cryptography. Okay, so prime numbers, they're not just some theoretical math puzzle. There are actual real-world uses for this stuff.
Oh, absolutely. For example, let's talk about online security. You know how important that is, right?
Huge, especially these days.
Exactly. Well, prime numbers, they're essential for that. They're the backbone of a lot of those encryption algorithms that we rely on every single day.
Get out of here. So you're telling me those little prime numbers are helping keep our online lives safe and secure?
You got it. It just goes to show something that might seem totally abstract, just a mathematical curiosity, can turn out to have these incredibly important uses in the real world.
This has been mind-blowing. We started with simple multiplication tables and ended up talking about like the nature of randomness, the limits of what we can know, and even the security of our online lives. It really makes you appreciate the beauty and power of math, even when it can't solve every single mystery out there.
It's true. The pursuit of understanding these prime numbers, it's been a source of challenge and inspiration for mathematicians forever, and something tells me it's going to stay that way for a long, long time. Who knows? Maybe someday someone will crack the code, or maybe, just maybe, the beauty lies in the journey itself.
Or maybe those prime numbers, they'll always hold on to a little bit of that mystery, always reminding us that there's always something new to discover in this incredible world of numbers. Thanks for joining us on this deep dive, everyone. We'll leave you to ponder the wonders of those prime numbers and that never-ending quest for the truth in mathematics.